continuation of last year's. And you're on.
Let's see. Okay. Thanks so much, everybody, for coming. Thanks, Harvey, for having me again. I don't know who's been here last year. It was already a 2-hour session we did in the spring of 2011. And Harvey asked me to come back and see how things are performing. We have a house basically which we built, we moved into in February of last year, so we have 1 year's worth of data. So we're looking at measured performance. You got a few more people coming in, so maybe we should give it just a minute for them to have a chance to sit down. I would be curious to know how many people have been last year at the, I see some hands, quite a few. What's the kind of professions we have here? Architects? 1 architect? 2? Okay. How about builders? Engineers? Okay. And then what's the rest?
Home builders.
Home builders? Just people interested?
Energy graders, suppliers.
Suppliers. Yeah, there we go. Suppliers. Okay. Well, my background is basically I'm a home builder. I have a design build company in Fairbanks for about 12 years. And I work quite a bit with the research center. For the last 7 years, I have kind of become obsessed with energy and how to build high efficient buildings in our northern climates. And especially the last few years have been quite a roller coaster ride for me. And I believe we need to change, so that's my personal mission. Why is measured performance really the crux? You know, we can build buildings like this, but we really have to look back after a year and figure out, does this really make sense? And cost is really the driving factor for most of these projects. How do we build buildings which reach almost zero energy in our climate without spending so much money that it doesn't make any sense? So if we're looking at the Sunrise project, basically, that was, to me, more or less a research project. It was a personal house I built starting in 2010. I finished it in February of 2011. It's my personal family home, a new house I moved in with my family, and we have 2 kids who are living with us and my wife. And it was basically a goal of trying many different systems, and in the end, you know, can we reach a building in this extreme climate which reaches zero energy? So there were a lot of lofty goals for this building, and anybody in here is familiar with passive house design? Is that, if you listened to me before, you know about it. It's basically, PH stands for passive house. Passive house is a German building standard which was developed about 20 years ago, and it's a scientifically based design goal for buildings to reach energy efficiency level of 80 to 85% above basically today's requirements. It's really a set of numbers we're trying to achieve with energy modeling, and these numbers don't change anywhere in the world. So a passive house in Germany is trying to achieve the same numbers as in Fairbanks, Alaska. However, the insulation and the challenges to reach it is much bigger here. So we have annual heat storage. That is something which I believe we'll have to look into for our climates, because we have a problem in the wintertime. There's no sun, there's no energy. When we need it the most, we have no energy available. We have an abundance of energy in the summer, but none in the winter. And then I wanted to have no fossil fuels in this building, so no oil tank, no propane. It's hooked up to the grid, so we have electricity, of course, but no other combustion basically within the building. I wanted to reach zero energy. What is zero energy? Zero energy basically is just a number game. Within 1 year, we are producing enough energy on site to offset the energy consumption of the building. and that gets us to 0. It's kind of a pretty iffy term, in my opinion, especially if we are on the grid where we're selling in the summer excess energy to the grid and then buying it back in the wintertime. But where's the energy coming from? There's a lot of questions. To me, in general, the goal should be to get the building down to absolute minimum as far as consumption is concerned. And then we're looking at no conventional heating system and no vapor barrier basically in the wall system which we used on this building, a prototype wall system, a diffusion open wall. We're going to talk about this later a little bit more. Thermal shutters basically, that is to me really the crux for energy efficient buildings in far north countries. Thermal shutters is the missing link we're having right now. We also will talk about that quite some more. And then we had no backups in the house. So if we do this right. And like I said, I mean, I moved in there with my family, with my kids. So this is not just, you know, a cabin. It was supposed to be a home first and foremost. However, I consider it as my personal lab. I didn't get any financing for building this prototype building. However, Alaska Housing generously gave us money to the research center to monitor the building. So we have an excessive monitoring system throughout the whole building, envelope basically from foundation over the diffusion open wall, over all of the other systems. Basically, we have very good data to make conclusions. Is this making sense or not? So just a recap as a quick reminder, what we do to reach these kind of levels. Insulation values basically in the walls, we had R75. And I forgot to mention this. This presentation will be posted on my webpage, on ACAT's webpage. So you don't need to worry about taking pictures or writing these values down. You're more than happy to download it and keep it on your file. The roof insulation was R115, and then the slab insulation R63. I established these values basically from historical data on buildings we've done before, and in addition, PHPP, basically the modeling software for Passive House, which kind of gives us these guidelines. What do we need to do to reach these levels of efficiency? In this building, we use cellulose, basically very low embodied energy insulation material. It's very cheap, locally available. It's made in Wasilla from recycled newspaper. And we used about 12 tons of insulation on this building. Yep.
What's the machine?
This is Enforce 4. It's basically a machine I purchased to blow this.
Insulation blower?
It's an insulation blower, yeah. We'll talk about some of this more here later too. Then the big crux on the whole project, really to get it to the level where it needed to be, was seasonal storage. This is not the first project I've done. I've chipped away on this for 3 years prior with different other buildings we tried. It's a very controversial topic. There's a big movement in Europe. It's called Sonnenhaus, where they're building buildings just like this. However, in our climate, it's a little different. And it's very expensive what they're doing in Germany. Average tanks are in the $54,000 to $60,000 range. So how is this feasible in our climate? How can we sell it to people and provide solutions? So I was just trying to come up with some more affordable ideas. So I just used basically a 5,000-gallon old stainless, an old fuel tank, which we cleaned up, retrofitted, and we'll talk about how we went about this. And now we're looking at 1 year later. This has kind of been a rough ride, and a lot of things have gone right, a lot of things have gone wrong. It was an extremely challenging project, and it took a lot of thought and a lot of figuring out, and that's kind of how I feel today. So it's a long road to really figure out all of these systems, and I'm not claiming that I have all the answers, but I'm sure trying, and that's, I think, all we can do. So let's look at facts over fiction, what worked, what didn't work. We started out with an energy model. Like I said before, we're using Passive House software, which is basically the software package developed by the Passive House Institute in Darmstadt in Germany. It's been refined over many years, and it's the #1 used energy tool right now in Europe to measure performance in pre-construction on the design side. The key here really is we design the building, we model the building, and we optimize the building before we build it. And that is a big process. It takes time, but if we're looking at an 80-year lifespan of a building, it's really nothing. It's very, very beneficial to do that. So we monitored, we estimated basically the energy consumption to be at 4.38 kilobitu's per square foot per year. What does this really mean? It means basically a 90% reduction over what we would consider a normal building, is what my goal was on this. Yep.
How many heating degree days are you?
It's 14,000 heating degree days. Yep. Yeah, I mean, this building is in Fairbanks, so. And
Is that in Fahrenheit or Celsius?
this,
Your heating degree days?
that's in Fahrenheit. Yep. 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 No, it's in Fahrenheit. I put some kilowatt hours in there because I just talked in Europe. I just came back from Europe, so there's a bunch of conversions on there. But basically, the model, gives us a benchmark which we need to achieve for passive house, which is 4.75 kiloBTUs per square foot per year, or 15 kilowatt per square meter. That's basically our target range as far as heating demand goes. And air tightness is the #2 number here. The 0.6 is our benchmark. I personally believe for very cold climates like here, we should set that benchmark even lower. I'm trying to shoot for 0.4 right now. Energy and air tightness is really closely correlated. And then primary energy, basically that's the total energy consumption, electricity and all of the other things combined. And then cooling for us in our climate is really not a big challenge. So energy rating at the end of the project in Alaska, we have through Alaska Housing, basically the 5-Star Plus program. So, as you can see, we had 100 points, so there is no more than 100 points. If we have 110, nobody knows. The software is not geared at all at high efficient buildings. We're still stuck in the 80s as far as how we're looking at buildings. And it's clearly showed on this energy rating, basically, which was done from a certified rater at the end of the project, that we don't know how to rate these buildings here just yet, which is sad because we really should build buildings like this. And then, of course, a year later, it's very simple for us to figure out, what did we consume and how much electricity did we use. I used quite a bit more electricity than I wanted. One of the main things I completely forgot about was plugging in cars in the wintertime on the energy model. We did really well in the summer, but as soon as the winter hit, and at Fairbanks, we had a very cold winter this year. We already hit 50 below in November, which I've never seen before. And then, of course, if you plug in 2 cars, that is a huge extra load on the building. I don't know how I forgot about that too, but. So we consumed for the first year about 6,480 kilowatts, which is, not bad, but it's more than I wanted to be for the first year. So there's quite a bit of optimization I'm going to have to do to reach my goal, which was in the 5 kW range. I have a lot of leverage still in lighting, where I kind of spent not as much money as I wanted because I ran out of money at the end of the project. So with some better LED lighting, which we're going to upgrade to, will help. And then figuring out what to do with my cars. Essential tools, basically, which we use to start off with. We extensively tried to model the wall system, which is the Fusion Open with Woofy, which is a professional software program developed in Germany from the Fraunhofer Institute. And then Therm basically was developed by Berkeley National Laboratories. That's used for thermal bridging. And then during the 1-year period, I went ahead, spent quite a bit of time with thermal imaging, trying to figure out settling in the walls with the cellulose, thermal bridging, hidden thermal bridges, things which you just don't see with a regular eye, you know, for optimization. I'm very, very big on indoor air quality, so we spend quite a bit of time monitoring that. And then, of course, blower door test. You know, we blower door test several times during construction to reach the air tightness level. And then at the end of the project, and then I always do one year later to see, you know, how is this really resilient? How is it performing a year later? And that's where we use the anemometer too to measure these very low pressures basically on pressurization. Blower door, most people nowadays are familiar. You know, we basically place it in the entry door. We depressurize the house at 50 Pascal air exchange, and we measure basically the volume of the house compared to how much are we drawing out basically small leaks. And to reach passive house at 0.6 is difficult when one starts out, but for us it's really not a problem anymore to reach these levels. It's just the building system, the way we go about it. In Europe there's a whole trade now basically for air tightness. You know, it's like a carpenter here. It's an air sealing trade basically, where people go to school and that's all they do, they air seal buildings basically.
In retrofit or?
And either or, yeah. New construction or retrofit. I mean, United States of America, unfortunately, is the only country left in the world which does not place high interest on air tightness on new construction or on retrofits. You know, our current energy code, the new revision, is still looking for 7.0 air exchange at 50. So we're looking at 0.6. That's pretty sad, especially in our climate where energy, that's the cheapest way to save energy, really. And then in this building, we have an extensive data logging system. Cold Climate Housing Research Center has the grant basically from Alaska Housing to monitor all of the systems. And there's many, many sensors which are placed everywhere to figure out what works, what doesn't work. Unfortunately, there's a problem with building science, with monitoring buildings. It takes time. You know, we're here a year later. Do I have all the results I want? No. There's so much data that needs to be analyzed. People don't have the time. Everybody seems to be maxed out with many, many projects. So, you know, I wish I had 100% of all of the data from the first year. I don't. And it takes time to figure all of these things out. So let's look at the building. You know, how are we really doing now a year later? We've basically went 275 days, 100% solar on this building, which I think is fairly good for where we are in Fairbanks. That's 9 months basically without any supplement. And the crux about it really is this. You know, if you're looking at a light bulb, is this something energy efficient? Old incandescent light bulb. But if I'm telling you that I made all of this energy with half a light bulb, with 48 watts, that's pretty amazing. So we are heating the building for 9 months. We make hot water for a family of 4 for 9 months with 48 watts. It's pretty incredible. And then, of course, we have the 3 months in Fairbanks especially, where we have no sun. There's hardly any solar irradiation. Mid-November, we're basically losing it completely. And we have not made any heat off the collectors ending in 3rd of November. And this year was a little longer. We started last year up at the 2nd of February. This winter was a lot colder, and it took until 9th of February until we got completely off wood, basically. So we burned this winter in our house 1.5 quarts of wood, which is kind of what I estimated. To put that in perspective, that's 22.5 million BTUs of energy. That's equivalent to 180 gallons of oil, heating oil. Most people understand that a little bit better. So for a 14,000 heating degree climate, for the dead of winter at 40 below, especially this winter, which was very, very cold, I think that's pretty remarkable. This picture here is the thermal image of my masonry heater. I just want to point out this is actually a picture taken into the window against the thermal shutter, reflecting the heat back into the building, which is pretty neat to see. how well that functioned. And also that's basically the fireboxes. The rest of the heater, one hardly sees any heat coming off, which is very important in a regular wood heat, in a normal firebox. You would completely overheat in a building like this because it's so super insulated. However, with a masonry heater, we have so much mass that it radiates out slowly. So here, thermal image, again, there's a lot of heat, but only a slow radiation of heat out of the building. I was a little worried about it. This is a 2-story building, 3 bedrooms, upstairs, doors, all of these things which make heat distribution difficult. I wasn't so sure how is this going to work with just the masonry downstairs for the main heat in the winter without anything else. But it was really never a problem. And we fired it usually once in the morning and once in the evening. And at 4.32 BTUs per hour, basically, we didn't have a whole lot of heat demand. So if you're looking back at our energy rating, estimated with 3 quarts, we only used half of that. Also electricity, about 40% less. I just want to point this out that this software program, AK Warm, basically for buildings, especially high-efficient buildings, is completely unsuitable. It's a very good software programs in the 80s, but nowadays we should really come up with some better means of rating these buildings. If we're looking at this picture here, I took this on the 19th of February. This is 10 days after I stopped heating basically my house in Fairbanks. So if you look outside, there's, it's cold. We still had 34 below temperatures at night. But I haven't heated since the 9th of February, basically. We're maintaining a even temperature. This is passive solar. There's no fire burning anymore. We are collecting heat for domestic hot water, but the only real heat in the building is through passive solar for already over a month. And it's very cold still outside. But these few hours of sunshine provide us all the energy we need. What's with this number here? Anybody want to comment on that? The upper big number?
Relatively many.
Yeah. What strikes you about that?
It's low.
It's low?
It's very high.
It's high, it's low?
For a house at 0.5.
Okay, well, let's vote. So we're looking at a climate in Fairbanks where we're dealing with 40 below temperatures. What's the problem with 40 below air? There's nothing left. At under 40 below, there's no moisture left, period. So one of the bigger challenges we face for healthy buildings in Fairbanks is how do we keep healthy indoor environments? We need to maintain, in my opinion, about 40% relative humidity for human health. However, in any other building I've built before, in the dead of winter, we're running about 20%, 50% less. Which is a huge problem. We're bringing this cold air in. How do we maintain in a building which is completely wrapped in a plastic back on the inside? How do we maintain healthy indoor climate? With this building, I was able to achieve 40% throughout the whole winter, no problem at all. Why? Because of the diffusion open wall, because of all of the humidity storage we have within the building. So that was very neat to see how well that actually worked. And to me, that's a huge plus.
So you're talking about humidity storage in the wall cavity.
We'll talk about this here in a second with some sensor data too. But just to point this out, this is, to me, just simply amazing. Imagine a building which functions like that by itself, just by sunlight. There's no maintenance, there's nothing. This is just purely passive. The building performs as it should for our climate. And then, of course, it's a house we live in, where my family lives, where we live, play, and enjoy ourselves. I have little kids, and they run around barefoot. This is not, sub-freezing house. This is very comfortable. And to me, really, the main thing about this building and other buildings we've built meanwhile is, it just gives you a much better comfort level than a normal house. It's not just about energy, it's about the health factor, it's about what makes a house truly livable for us. And that was really, to me, the most surprising part about the whole project. Something I never really thought about too much, wasn't really high on the agenda either, but that's really where we are right now. My kids come down the stairs, they look outside, oh, it's sunny, and they have a little dance, house is going to be warm. The totally different perspective on living, and it's more of a living building, really, than just a regular house. So my lofty goals, a year later, I have not certified this building as passive house. My numbers show that I could, and I probably will, but I want to back that up with data because there's no other house in the world right now that far north which is passive house certified. So it's kind of like political issues. And your heat storage worked really, really well. No fossil fuels worked well. I'm not at zero energy. I have no photovoltaic system up yet. I would need a 6 kW photovoltaic system. The only reason I haven't put that up is because I ran out of money. Most people can relate to that, but that's really the missing link and something I'm hoping to get up this summer, but I said that last summer. It's just really a money issue. With a 6 kW system, I'm very confident we could get to a zero energy level. And then we have all of the other issues, other points which we really had no issues with, like the no backup. Did we ever have an issue with having no hot water? No. Anytime we fired a masonry heater, it produces plenty of hot water basically at the same time for a family of 4. We have unlimited hot water for 9 months out of the year. We can open the faucets basically on 2 bathtubs for over an hour in the summer without running out of hot water. We can store hot water for 6 weeks. So if there's no sun for 6 weeks, it doesn't matter to us. So it's pretty amazing to see, how much the system really produced, how easy it produced, and with how little energy. So to me, really the key out of this whole thing was that I will never look at a building the same way. I see so much potential we can do in buildings. We haven't even scratched the surface. Just looking at the performance of this building and other buildings we've built meanwhile, if we put our minds together and come up with a little bit better strategies, we can build, even in our climate, extremely well buildings. And I think that's really what we need to start realizing. We have to really come to terms with it, that we need to live with our Arctic sun and create systems which will allow us to do this. The key problem is heat for us in the wintertime, and somehow we have to figure out alternative energies to do this. So how do we create sustainable shelters in an unsustainable world? How do we go from here, where we have been, where we don't want to go back to, because that was maybe sustainable then, but it's not comfortable for us now, to a place like this. When we run out of energy, when we run out of resources, how do we combine them? And we are here very, very fortunate. We are very rich as far as land goes, as far as beauty goes. I travel a lot, and I've been originally born in Germany. I guided all over the world. I've been to many, many countries. Just got back from northern Norway, but there's no place like Alaska to me. This is the most beautiful place on earth, and we have so much beauty. However, in the wintertime, we have so much harshness. The top of Denali in the dead of winter, it's super cold. And how do we sustain our communities here with this problem we're having now? We're running short. We're not really running short, but we're running out of money to afford it. Unfortunately, this is where we are, if you want to believe it or not. But where are we going? What's our plan right now? How are we coping with $4 or $5 of heating oil as an average person? We just can't. I know a lot of people in Fairbanks right now, which already this winter took out second mortgages to heat their house. That's just completely unsustainable. And then, of course, we have other issues. Right now to the research center, there's 184 of our remote communities which effectively are on a red list for climate change, on issues which they're dealing with on everyday basis. This is Shishmaref, which is being evacuated more or less at the moment. For the last few years, they're fighting these problems. Huge erosion, you know, your house falling apart because the winter, basically the ice is just not there anymore to sustain the pounding of the sea, and you know, I wouldn't want to live in here. But this is basically where we are, and you know, from the last frontier, we already have become the first frontier. All of these extreme climate differentials we see worldwide, we are on the leading front of taking these effects. The farther north you go, the more these effects are already in place. And we have to come up with solutions. I really, really believe we're out of time. And we are already in free fall. All of these problems, you know, we keep talking about it, but the reality of it is we're already in the midst of it. We just don't know when we land. And pretty soon, and if I say soon, maybe in 50 years, energy, water, and air will be really our main issues we will be dealing with, if we want to or not. And you know, this is what we're doing right now. How can we live sustainable in a northern environment like here? We're just turning up the heat. We can heat any building, any society with enough heat. And energy was always cheap, so we didn't have a problem supplying enough heat to a building, you know, like this building here. If we just turn up the heat, turn up the supply of energy, then we're all comfortable. You know, it's cold outside, but we're very comfortable inside. The problem is we're running out of heat. So if we're looking at the United States energy usage, really, just to put a perspective on it, why are we really concerning ourselves with buildings? Because it's really the biggest consumer of energy. Most people don't realize that. They think that transportation is the problem, but it's really buildings. Buildings is the low-hanging fruit where we can gain the most. And then if we're looking at you know, where we are on average, this is our, you know, highly acclaimed LEED homes, which is kind of like the current trend, where we're looking at 25 to 35% efficiency increase, which in my opinion is a total loss of possibility of an opportunity. This is passive house. This is, I think, a very feasible number. We can call it anything we want, but what we want to achieve is at least 80% reduction in consumption. And then ideally, of course, net zero, which is expensive still because we need to place renewable energies on the building. However, this here is very achievable. You know, a building like this is a payback right now, in my opinion, at Fairbanks of 4.8 years. So it's a total no-brainer. Going to net zero is a little bit more.
Are the German and Danish figures achieved with the infiltration standards you described?
Yeah. I mean, there's, in Germany, there's over 20,000 certified buildings. You know, we have 13 certified in the US right now.
Passive houses.
Passive houses, yeah. Yeah. I mean, we haven't even scratched the surface as far as the United States goes. We're really not into that yet. But
question?
Yep.
Can you just on that last slide, how does that compare to, you had your units, you had 1,000 BTUs, 1 million BTUs per square foot?
As far as my building?
I'm just the conversion between the two.
Yeah, I mean, we're here. I mean, we're 15 kilowatts per hour basically is what per square meter is what Passive House prescribes. I was at 13.62, so we're definitely at Passive House level. So just to recap, Passive House, you know, there's really, it's all about insulation, air tightness, and reducing of primary energy demand. And then the big missing link from the 70s, when we already done all of that in the first oil crisis, ventilation. And we've built a lot of really super insulated buildings in the 70s. Older folks in here know all this. Passive House more or less was invented in the 70s in the United States and Canada. But we missed the important point that we need to ventilate very airtight buildings. And technology wasn't there, our knowledge wasn't there. We knew everything else on the building side, but we didn't understand how to ventilate properly, which lead to, you know, mold problems, moisture problems, very uncomfortable houses which started rotting away within 10 years. That's, at my opinion at least, why super insulation never really catched on here in the 70s. Not because it didn't work, but because we didn't understand ventilation. So if we're looking at this, what do we really need to do? I think we need to look at people, at health. Buildings are about people, not about buildings. People should be healthy before they're concerning themselves with energy. And it doesn't help us if we build something energy efficient wise, and then it kills us because it's unhealthy. Comfort is huge for us. It's more people are concerned about comfort than with their energy bill. Energy, and then of course money and embodied energy. If we're building highly efficient buildings, embodied energy, basically the energy it took to make the materials to build the building becomes much more intensive because we're using more materials. So that really needs to be taken into consideration. An example here would be the insulation material. If you're using a foam-based insulation material versus cellulose, that's a factor 64 in embodied energy. So that is huge as far as how much energy has been gone into the production. If you're looking at all of this, it's a huge maze. How do we make this all happen in modern buildings? Fit us, people, health, costs into something and make buildings which really function for us and for the future. And I really think that looking back and looking at some indigenous wisdom, what have we done 10,000 years ago when we lived here sustainably, helps us a lot, helped me a lot really to come to terms on how can we make buildings work. I believe iPhone 7 is not going to solve our energy crisis. This is where we're all excited about, but technology is not going to solve us these problems. It's more us realizing what's important. Really understanding again that we need to build buildings or systems which follow the laws of nature. If we build something which defines nature and the laws of physics, and we are surprised that it doesn't work, then I don't know. And that's what we do in a lot of buildings. It's very basic things, hot to cold, building science, the basic steps which are completely omitted oftentimes in the design and the construction of buildings. That's really where we need to start. And we need to think outside the box. It's like on my house, it would take my house about an 18 kW photovoltaic system to reach zero energy without heat storage. Very unfeasible, would never be able to be marketable. Where are we going to put a huge photovoltaic system like this? It's impossible. So seasonal heat storage with thermal collectors which are much more efficient, which solve the problem of heat first and foremost, I think is one of them examples of thinking outside the box. Simplicity, everything we do needs to be so simple that we can walk away from it. I can walk away from my house and not have to worry about heating. I can log in and can see I created 168 degrees of heat this morning, but I don't have to heat, I don't have to worry. I don't have anything which can go bad. The maintenance is very, very simple. And the simpler we can make these systems, the better. That's my main goal right now. How do we simplify this to make it cheaper? And I think the key thing to come to terms with is buildings are not about buildings. They're about people. They're about us. They're about people living in buildings, and especially in northern climates where we spend so much time indoors. That's really, really something we have to rethink, because the current trend is all about the building, the design, and not about the comfort and the health and the environment inside. And what makes us human and what's really important in the end of the day, where are we coming from and what makes us feel comfortable and healthy in a building? I think that's something we are not thinking about too much. And then I think this is my key lesson for the last year. I will never look at the sun the same way again since I live in my house. I have a smile on my face when I go outside and it's sunny because I know my house is charging up. It's free energy. And that's kind of a feeling, I guess, which is hard to describe. But it's really, I love the sun. And I have a complete different opinion about it now. And this is, I think, such a classic to be here in the BP energy system. It's like, you know, maybe I throw this up and I get thrown out. I don't know if everybody realized that 85% of all of the revenue of Alaska is produced by oil on the outside. The nice light banner they have going on. So this is really the problem. You know, this is our host right now. 85% of all the income of Alaska is right here. You know, he's looking for means of making money. And we're looking for means of energy. And he's right in our way. You know, we have everything available, even in our climate, to do whatever we need as a society as far as energy is concerned. But we are so focused on fossil fuels, because that's how our world works. That's how we make money, that we just don't believe that we can be a sustainable society on solar. But I'm totally convinced we could. So let's look at some basics. We're going to look at a lot of these graphs, so bear with me. They're a little bit mind-boggling when you look at them first. This is basically an energy model we've done on a building, not on my building, on a different building, to find basically the low-hanging fruit, what makes the most sense. So we take a baseline, basically, which would be this nebulous point. This is our energy model for the core building where we are right now after optimizing the building. And then now we see all of these white lines basically going all over the place, and we see basically a percent and a heat demand column left and right. So this is a sensitivity analysis basically to figure out what makes the most sense in a building to improve efficiency. Where's the easiest means of finding improvements. So if we're looking at this line here, you know, this makes a huge jump. That's basically the orientation of the building. So if we're looking at a building, you know, like right here, you know, if we want to collect passive solar gain, and we have the sun here, we put all of the windows there, there's a problem. We can't get the sun in here. So orientation, of course, makes a huge difference. Placement of windows, all of these things which are so logical, which on an average building we just don't do, they're really clearly shown here in this line. The reason why this is not down here is because right now the client decided to put this building at 189 degrees instead of 180, which would be optimum. That has site restrictions, which I think can be solved. So I'm sure they will go the other way, because this is still a lot of gain we can get for free. All of the other lines, you know, are basically, we're looking at slab insulation, wall insulation, roof insulation, all of the other things. And we will look at different lines here in a minute, but that's what all of the other lines are. You know, we're going basically, okay, baseline, 50% increase, 50% decrease, replacing 50% more insulation in the walls. What happens? You know, this would be wall insulation right here. So if we're increasing wall insulation, you know, that's our low-hanging fruit right now. That's where we see the easiest gain. And then, of course, orientation. Baseline is 180 degrees due south, optimum. And then shape and everything else would fall into that too. So if we're looking at the site, really we want to make sure we gain maximum passive solar gain. We have great tools available nowadays to do this really easily in real time on site. I use a solar eye, basically this little gizmo here, where we can go on the site and instantly with GPS and weather data basically from the local weather stations figure out exactly, you know, where's our optimum, where's our shading, where we can simulate, you know, how much vegetation do we have to take away, all of these things in real time. Very, very helpful. And that's really the first step. You know, before I design a building, I always go on the site. I always take readings and I figure out, you know, what's my baseline, the site. And then, of course, you know, we got to place windows where they belong, and we got to glaze them so we can capture the free energy, so the orientation of the building. The next big thing really is ventilation. Again, if you're looking at our chart, you know, we come straight down here, and that's overtaking wall insulation at the beginning. Why is this flat lining here? Anybody want to take a guess? That's basically 100% heat recovery ventilation. We can't go past 100%. So technology is an end. That's where it flatlines. But
Is the design value adjustment percentage, is that is percentage based on?
yeah, it's just a percentage. It's percentage basically on wall insulation. You know, you would look at an R80 baseline or an R79 or an R81 basically. That's how this model basically establishes this. It's a pretty simple logistical overlay on top of passive house.
Oh, so passive house provides the baseline for
Yep.
all these different factors.
Yeah. I'm sorry if that
That's
wasn't
the
clear.
inflection there in the
This is basically establish my baseline by doing the whole energy modeling in passive house. And then I create on top of that an additional model which gives me the opportunity to look in both directions. You know, if I go 50% this way or 50% that way, what happens to the building? What happens to my baseline? So that's basically how this is established. It's just an energy model on top of a model, energy model basically, just to find the low-hanging fruit. I spend a lot of time on this just for optimization ideas on, you know, how do we optimize buildings for our climate. Once we've done this once for the different climate regions, we will have much better, good answers for this. And we don't have to do this on every building, but right now I think there's a lot of value in this to figure out what makes the most sense.
Does this come out of the passive house software?
No, this is something we created in-house. Yeah. So why is ventilation so important? And I can't stress this enough. There's, you know, unfortunately, so many people don't realize we are really depending on good air. And we are, per day, taking 20,000 breaths. We consume 35 pounds of air, but we just don't know it. You know, it's something we just do. We can't see bad air. You know, if we could invent these magic goggles which will tell us all the bad things in the air, how, you know, low the humidity level is, all of these things which influence our health, our industry would be, you know, jumping 100% tomorrow. But we don't see it. It kills us slowly, and we have all of these problems in all of these buildings because we just simply don't know it. So ventilation is really important. I used a German HIV system in my building. The reason for that is that you cannot buy any really good, high-efficient heat recovery ventilators in North America right now, unfortunately. We are still kind of stuck as far as recovery goes in a fairly low level. These things are passive house certified. They're third-party, basically verified in Germany. And this unit has a combined ground heat exchanger which plugs onto this unit, where we are taking basically the heat of the ground to preheat incoming cold air, which is, you know, a huge problem for us at 50 below, bringing 50 below cold air into a heat recovery ventilator. What happens? You know, it shuts off. It goes in recycle mode because it freezes otherwise. You know, I mean, we've been able to get much better with this over the last 20 years, but we're by far not even close to where the units are in Europe right now. And this basically just takes a loop of 400 feet of PEX, 3/4-inch PEX with glycol, and runs it through the ground. I bury these loops about 12 feet down, and I run them under the septic systems below that to capture residual heat from the septics. And I'm able to at least get 42 degrees. Our core ground temperature in Fairbanks is 34 degrees. So, you know, instead of 50 below air, we have a plate exchanger in here which preheats that incoming air to 40 degrees. So instead of 50 below, we're always looking at a baseline of 40 degrees at least, which of course is huge. You know, at really cold temperatures, we're still maintaining 2 to 3 degrees differential between supply and return. Why is this so crucial?
Comfort.
It's comfort, for sure. If you're looking at energy, you know, anything we're dumping out of the building, we have to replace. So any heat which we are, through ventilation, removing from the building, we have to reheat. And the more we can recover, basically, by a heat recovery ventilator, which takes the incoming cold air and preheats that with outgoing warm air, the higher our efficiency is, the greater our efficiency on the building. And this is really the low-hanging fruit. Number one, for health, because it's very important. Comfort. If you have cold, drafty units, which is a big complaint on heat recovery ventilation, still in the dead of winter. Noise is another big part of that. There's much lower noise level on European units than what we have here. And that is really where we gain the most. On a public building, I've just finished the modeling on a small library project. That was really by far the greatest savings to going to European-based units, which we're specifically getting for this project because of the heat recovery ventilation. So this is really a no-brainer, something really our marketplace needs to catch up. This is some sensor data basically out of the ground, which we have several sensors placed by the outside heat loop. One concern was, if we're taking this energy out of the ground, will we create permafrost in Fairbanks? And that's really not the case. Our temperature actually has gone up quite a ways. So that's pretty interesting. We will see a whole bunch more of these. We could talk about any of these for hours. We don't have the time, but if you're really interested in this, look at Cold Climate for the report on this. There will be a report about a ventilation system. There will be a report about a wall system, a third party, not from me, but from the research center, so not a sales trip. They will have also the data sets available. Our goal right now is to get everything live streaming so people can go on and see it. And there will be explanations about some of these.
Do you know when those reports will be available?
No, I unfortunately don't. It's kind of out of my control. And everybody's, I'm extremely busy. The research center is extremely busy, and finding time is so difficult.
Like 6 months or a year or 2 years?
I said last year it's going to be 6 months, and now we are 6 months later of that, and we still don't have anything. Do I have a good answer? No. I hope we have them out, by the summer, but I can't tell you, unfortunately.
On your last slide, you had permafrost at 6 feet?
No. This is basically, forget about this baseline before it was run out. This is really what we're looking at. We didn't have.
Are you on permafrost?
No, we are not on permafrost. But our level between 34 degrees core temperature and permafrost, the margin is very slim. So if you with a heat pump extract a little bit extra heat, the concern is in our area that we're creating artificially permafrost by lowering that threshold. That's really, but I'm not on permafrost.
Why are you concerned about creating it?
Why are we concerned about it? No, because that's not necessarily a good thing on a building.
Oh, it would then suck heat out of your floor. Okay.
Yeah.
But for stability, it's no problem.
Right. For ventilation, I also want to mention living walls and hydrocultures within buildings. This is something I started doing for the last 2 years. And I see really great success in utilizing plants basically in our climate to introduce additional relative humidity, and also for air purification, where we spend so much time indoors, especially in office buildings or in buildings where we have a lot of electronics. They can really help a lot on creating a much healthier living indoor quality, basically. And we pretty much do this on every new building now we design and build. We integrate hydroculture, so you only need to water that once every 4 weeks. There is no soil involved. It's all more or less automated, and all of the bad parts are gone, and we can utilize specific plants for taking out volatiles or certain other things out of the air. It's a very good system, and I can only heartily recommend it. Low-hanging fruit, something which we haven't really tapped into too much either. Water recycling, on an average building, we're looking at a 20 million BTU use of energy to make hot water. What are we doing with it? Goes down the drain, it's gone. If we somehow can, contain it within buildings, especially bigger buildings, this is really where we're going to be able to save a lot of energy.
Does that have potential to replace the HRV?
Well, no. We still somehow need to introduce fresh oxygen. In a way, maybe, but we're definitely not there. Here we're looking at the same thing. We're just looking at the wall insulation, basically, as the second item. This here was ventilation. This here is insulation. If we run this all the way out, it goes way out, so insulation really makes sense. If you put no insulation in the building in Fairbanks, Alaska, it's really cold. I don't need computer modeling for this, but this is pretty interesting, to see how dominant wall insulation really is. And why is that? Why is wall insulation much more dominant than roof and slab?
Area.
Is it surface area?
Yep. Exactly. It's the most surface to volume ratio basically on the whole building. Much more wall than roof, much more wall than the foundation. So in the wall, our wall is really our best trend. For this building, I basically built this prototype diffusion open wall system. I call it the Arctic wall, but we can call it anything. It's really nothing else other than a remote or a persistent out insulation material which we replaced on a remote, basically, which is built with foam, sheet good foam or sprayed-on foam. We replaced that with something more renewable, with dense packed cellulose. But the principle is still the same. We have basically our core structure on the inside. That's our building. And then everything you see on the outside here is just fluff. That's the insulation. That's the down part that we're placing on the outside. It's cold on the outside. We need to have the insulation on the outside. And this is all dense packed, and then in the roof, it's also dense packed cellulose. It's a cold roof. The insulation sits right on top. So it's completely wrapping the insulation. So the ground insulation continues up here and then all the way around the building. So there's no cold bridge anywhere. And then out here is the wing insulation that basically helps from keeping the frost to go under the building in the winter time when it cools down.
What supports that outer wall has to have some mass, right?
The structure is really, the structure is right here. And then you see the gusset plates. The gusset plates basically, so all of the weight is supported off the main building. It's not really supported on the main building supports it. So we're basically just hanging it off the building. And it's a lot of weight, but it's just an engineering, a math question. It works really well. And then we either, like here, this is my standard detail right now. We do an 8-inch slab, so we don't have to worry about any footings anymore. Just labor cost-wise, extra heat storage is much quicker. We just form up an 8-inch slab all the way around. We don't place any more footings anywhere, and we just pour it, and it's very quick, very easy, and it gives it additional heat storage, basically.
So then your insulation, you don't worry about getting below frost depth because you're so well insulated.
Yep. Yeah, again, this is, shallow frost protected foundation systems in general place no insulation under the footings, a total heat loss for a high efficient building. It took many years for me to consider, get this, engineers to sign off on this, but it's really, I've never seen any issues. We have sensors which show the same thing. The minute we are basically having enough insulation and we are placing it on a non-frost susceptible soil, this is compacted gravel, so there is no frost heaving because it's not a wet soil. If this would be wet clay, I would be very worried about it, but I would replace it with gravel. Yeah.
What is that exterior material level with the slab to the very exterior, that vertical, down below there?
This here?
No, below. Right off to the left a little bit.
This here?
No, the one right there. The one in between the two, between the outside insulation and the inside insulation.
Oh, okay, here.
No, further outward and downward.
The purple.
No, but come down a little bit.
Okay, I'm lost.
Those two large vertical pieces, if you come closer to you just a little bit. Right there.
Yeah.
This is just foam.
Oh,
Oh yeah, no, this is just the same like here. It's, under the footing we use a 25 psi foam, and then that's what we wrap up. And then we had the insul foam make us some pieces now which are shaped like this, where it's just like a Lego system.
125 psi?
Yeah. Makes it very fast. You don't even need foam boards. 25 psi, yeah, correct. Again, depends on the size of the building. If you have multiple stories on top, more weight, you might have to go up to something more. Why a diffusion open wall system? Why did I want to try this? there's multiple issues. The main thing for me was the drying potential in any direction. You know, we cannot build anything perfect. Over time, we will get moisture in any wall system. If we're trapping it in something which cannot dry out, if we have a problem, we create mold. As long as it can dry, there is no real issue. And then it functions like a Gore-Tex jacket. You know, in closing, we have this for many, many years. In Europe, this is very common too. However, in North America, you know, we're very, very adamant about having something very impermeable on the inside on a cold climate. Building code subscribes that too. You know, like in Fairbanks, we're required by building code to have a class 1 vapor barrier, which, you know, is like an equivalent to a pulley, a 6 mil pulley. What I'm using basically is plywood, CDX plywood. Time really is my main concern. Over 80 years lifespan of a building, moisture will get into this wall. It's ignorant for us to believe that we can build something completely perfect. If it can dry out, it's not an issue. If it can't, then it will, you know, split rocks over time.
Did you get that from the Baubiologie?
Yep.
Switzerland?
Yep. Yep. Baubiology in Europe, it's very big for many years, and there's many other points which flow into it. Yep. If we're looking at walls or building systems in general, you know, as far as durability is concerned, durability is essential, otherwise building falls down. You know, temperature, relative humidity, and time is really what makes buildings stand or fall. And as long as we control these, you know, if we don't control and time comes into play 5 years later, we open the wall, we have mold, we have dry rot, which I've seen on a lot of buildings. If we built it properly, you know, we have a building for 100 years. I mean, I looked at buildings which are 2,000 years old, wooden buildings, absolutely functioning. You know, if we keep the things which make walls fall apart out, nothing can happen. Air tightness, again, you know, this is really the big thing to understand. It's not about keeping moisture out. It's about how do we keep it out of the wall. Diffusion versus air transportation. And 99% of our wall fail rules is to air exfiltration. You know, if we're looking at one little hole here in a piece of sheetrock, which we will have by placing just a nail basically on and a picture on the wall, a homeowner moving into a house. We have 6 mil vapor barrier, we put a nail into it, hang a picture up, we have a little hole. Through air exfiltration, you know, we have different pressure systems within the building and the outside, so we're creating ideal conditions for vapor drive. We're creating 30 quarts of water. If we're looking at diffusion, you know, we're only looking at 1/3 of a quart. So this is really the thing to understand. You know, we're not building a breathable wall, we're building a diffusion open wall where we allow this, but we eliminate this by being very airtight. It needs to be very, very airtight. Airtightness is really the key. It's not the vapor barrier which we prescribed. We had a lot of buildings fail in the 60s. That's why we came up with the idea we need to place a Band-Aid on this, which is that 6 mil vapor barrier, class 1 vapor barrier. However, we cannot install it perfectly the way it is, and we are creating still a lot of air exfiltration. And we're not placing any emphasis on air tightness. You know, Energy Code 7.0 still for air tightness. So once we're in a diffusion level, it's not an issue at all. So in this building, you know, this is a shut down the wall. Basically, you know, we're just dense packing the exterior. Why cellulose? What's so great about it? It has a very high density. It's very heavy, and it has therefore a high heat storage capacity. So we can store a lot of basically heat from the building within the wall, within the system itself. If you're looking at 12 tons, that's a lot of weight. There's a lot of density, there's a lot of heat storage capacity within the building, basically. So this is the wall basically built on the ground. On the first one, we built it completely different, but I built about 6 more like this last year, and we've really come up with a much better system. So everything is built on the ground. You're looking down basically on an exterior wall. You see the window bucks. And here, basically, it's not a hallway, it's really the wall. Some people say, oh, this is a hallway with no sheetrock. It's basically, you know, we're looking at this. This is the pressure boundary. Basically, this is our air tightness layer. We're using CDX plywood as our diffusion layer. It's wood, basically, so it can handle moisture. It has a perm rating of 0.6 when it's dry, about perm 1 once it gets a little bit more wet. And that's what allows us basically to diffuse moisture in each direction, which is very important going back to the relative humidity, storage capacity of the building. Settling is definitely a big question. You know, how do we keep this from settling in a wall like this? So,
how wide is this?
This is a 18-inch cavity right now. The beauty about this wall really is that we can create our value very simple, very easy, just by, you know, the gusset plates. The material basically it takes to build the wall is almost the same, going from 12 inches to 18 inches. Doing an R70 wall versus an R50 wall, you know, you're looking maybe at $800 difference in material costs. So it's very cheap as far as reaching these high-level R values. If you would do this, you know, with a with a spray foam type material or with a sheet gut material, the costs are exceptionally higher going to these higher levels. The material itself is cheap, and the only thing which really changes is that gusset plate, you know, the length of it. So for Anchorage, would we need, you know, 18 inches, or we would figure that out basically through the energy modeling. Yep.
Are you going to get a chance to talk about interior paints and exterior finishes on your wall system?
Yeah, a little bit. Yep. Yep. Again, you know, the key thing to understand is that plywood basically creates our boundary between inside and outside. All of the inside framing, which is the structural framing, becomes an interior wall. So we can run plumbing, we can run ventilation, everything else. I don't insulate most of them anymore because of costs. You know, we make this wider. Insulating one cavity versus two is much cheaper. You know, of course, it would be beneficial to insulate it too, but we don't need to. This is our thermal boundary. And this is very, very carefully air sealed. All done underground. It's fairly simple, really. And then now, you know, this is very much protected. No matter what you do on the inside, if you hang up a picture or whatever else, it doesn't, you know, put any holes into our pressure boundary, into this air tightness layer. This is a shot down from the attic into the wall, basically, being dense packed. And here you give a pretty good size comparison. This is my little girl. So we're having a 24-inch total thick wall. This is our standard wall. I haven't built anything else since last year. This is really our baseline wall now. It's very cost efficient, and it works extremely well. I'm using on the outside fabric from Europe, from Swiss, which has a very good permeability. It's a perm of 54, so it can shed moisture out really well. We have an airspace between the siding and the actual membrane to allow, again, for drying potential. So if we're looking at some sensor data, a lot of people were worried about this wall is going to rot away in 3 years because it's not going to work without a vapor barrier. If we're looking at the data, you know, we're not even close. I mean, we're well below 16% on our humidity level within the wall. So it functions really well.
It's the same design as a commercial roof, only vertical.
Yeah. Yeah.
Are any bathrooms on outside walls?
Yeah. Yeah. You're looking at it right there. Yep. Yeah, of course, we measured, especially all the wet areas, we measure carefully. Interesting thing is really to see how well this membrane works. You know, we're looking basically at a membrane, and we have one state of humidity and another state, and we have a very hygroscopic material with the cellulose, so it can soak it up and release it. If it's getting wet, it's a problem, but if it just gets to a certain point under the 16% range, it can store it and it can release it back in. And through the fusion, through the plywood, through the wood, basically, we can achieve this. And this is what we really see well on these slides. Again, you really need to look at the report for clarification on some of this, because we could talk about this all day. But what happens is we're fluctuating in between. We're creating humidity in buildings, and then we leave. no humidity is created. And the inside will take on the state of its next door neighbor. So if the wall has that storage capacity, we have usually in buildings, condensation on windows, wet dripping walls, because it has no place to go. It has no capacity to store temporarily moisture. And we have high humidity levels, and then we have very low humidity levels in buildings. That's just the way it is. We all come in here, we create humidity, relief, and then somehow this room has to deal with it. On a commercial building, it's a little different, but on a residence, it's the same principle. And really, with this wall, we were able to achieve 40% all year, even in the dead of winter. Yep.
If you decrease the permeability of your plywood by doing something like putting a traditional vapor barrier on it, what would happen, do you think?
Well, it's fairly simple. We would basically allow a drying potential to the outside.
Would that work?
Well, would it work? Yeah, probably. However, we would lose two things. We would lose the humidity storage capabilities of the building, which I think is very important. And then something which is talked about in biobiology in Europe quite a bit now is how do we balance ion counts from the air, the things which make us healthy, which, why we need to go outside, why we need to take on sunlight. How do we balance this on a building? It does not transfer to a 0.1 vapor barrier. So, if we have electronics as an example, they create a lot of negative ions in the air. They would balance out if it could travel through diffusion to a wall system. If we are locking it out, basically it wouldn't be able to do that anymore.
So you think your indoor air quality may be improved by having...
Yeah, absolutely. Yeah, a diffusion open wall is really, to me, the main reason, the main motivation is health, human health. And then second of all, of course, the building. But people first, it's about us. So there's many things to look at. And unfortunately, the more you look into it, the more complicated it becomes.
Your wall's only breathing from the very outside. It's not breathing from the outside of the sheeting.
Well, we shouldn't even talk about breathing in walls because walls don't breathe. It's diffusion. But we allow diffusion all the way to the wall. And
from the outside of the sheeting?
No, it's diffusion open. No, there is no vapor barrier anywhere. It's just a pressure boundary. But it can react all the way through. And I see moisture shedding out on the outside in the dead of winter on my building.
Jack's doing that same thing, but he's putting a vapor barrier on the outside of the sheeting and then layering up 3 layers of 2-inch blue board.
Right. Yeah, which only has a drying potential to the inside. There is no drying potential to the outside. However, with foam, we're not worried about foam. You can hose it down with a water hose, and it's not an issue. It's not hygroscopic. It's a completely different system, really. We're not diffusion open in any direction, only in one. In certain climates, like in Juneau, as an example, this wall would not be the ideal solution. I would definitely replace the cellulose with rock wool or with foam. Foam, has been done many times in Juneau where we are limiting basically the drying potential.
If you're 40% humidity inside and 0 basically relative to the outside, aren't you just driving that moisture into that wall?
Well, we have so much distance to travel, and we're changing continuously on the inside. That's the thing to remember. Think about it as a sponge. It finds its closest neighbor, outside or inside. That's what it reacts to.
Cellulose doesn't really like to dry out quickly.
Well, but it works. Yeah, I mean, you see that. I mean, this data set's out of the wall. So, yeah. But yeah, it was certainly a big concern. So.
Sorry, why is the HRV not taking care of the problems of air quality? You mentioned ions, which I don't know anything about.
It does, certainly does, absolutely. But not in a natural state.
Right, okay, gotcha.
But yeah, it does. We're bringing outside air in, and we're replacing.
So long as you have clean outside air, you're good to go on that.
Yeah. Yep. But it's on a bigger scale. It's a natural balance, basically.
Not passive,
Yeah, it's a natural balance. That's really what it comes down to. If we're looking at this, this is from a bedroom wall on the south side. We see a huge scatter basically within the wall. We're looking basically at huge variations of transfer within the wall. Why do we see this on the south-facing wall versus, on the other? This is towards the west. Here, basically, what we're looking at is the heat storage capacity of this wall in reaction to, again, the outside. The heat storage capacity on this gives us a time delay, basically, as far as how long does it take energy to travel from the inside to the outside. We're losing heat in a building because it's cold on the outside, it's warm on the inside. So by physics, by laws of nature, it's going to go from warm to cold, and we're slowing it down with insulation. How long does it take, basically? If this would be a regular foam-based wall, there's maybe 6 hours of time delay. On a cellulose wall, what we're seeing is 13 to 14 hours time delay for the same amount of insulation because of the density and the heat storage capacity. So what happens on the south-facing side, if the sun comes up, the outer surface of the wall becomes warmer. And then we see these huge fluctuations where the temperature, BTUs don't care, inside or outside. They only care about temperature, so they get confused. And the beauty is sometimes we don't lose any BTUs on this whole wall face because the outside wall warms up so much that the flow of energy is returned, basically. It's pretty interesting. So that's decremental A, basically, is what we're looking at. Going back to your question, if you're looking at this for relative humidity, isn't that just driving out? Shouldn't it just be driving out? Here, the thing to remember is we're looking at such a thick wall that, it always looks at its closest neighbor. So the inside, this is red. Let's forget about this because this is building drying out. But if you're looking at this, see this is inside, the green is outside, and the blue is outside of the CDX. This correlates really to what it's seeing on the outside of the wall. So if you're having a very high relative humidity on the outside of a thick wall like this, it doesn't care what the inside is. The outside will take on that state, which is very important to remember for wet climates. On a thick wall like this, the physics is completely different than on a regular sized wall. The drying potential from the inside is just not there anymore. So we're looking basically at a sponge on the outside. It's a sorbation, and it will take on the outside. If you place a piece of wood on the dirt, it will take on the humidity from the ground. If we're placing it on top of some stickers and let airflow under it, it will be much better, but it will still try to soak up that humidity level, basically, relative humidity from the outside. So if we place like a wooden structure on the outside of a 24-inch thick wall in Juneau, that wood over 5 years probably will rot because it will not dry. It won't have drying potential. It's too far removed from the inside, no drying potential, enough from the heat basically of the building because the building is super insulated. It's very different than on a regular 2x6 wall, so something to keep in mind.
So, you're saying on a regular 2x6 wall in Juneau?
Yeah, let's put it this way. We built a shitty building. We crank up the heat. We always have enough heat from the building drying this out. Now we're saying, let's build a super insulated building. We place it on the outside. We only have very little heat we're placing in here. So the outside doesn't get anything from here.
It's ambient outside all the time.
Right.
Yeah.
So it will only care about what's happening here. So we need something non-hygroscopic on the outside for climates like that and in buildings like this.
Or weather protected.
Right. Like rock wool would be ideal for a climate like that.
But isn't it all about keeping the dew point out of the structure?
Yeah. Yeah, certainly. Yep. But nevertheless, you have, like on this wall, you have a wooden structure on the outside removed by 18 inches from the inside core. That's my point. That outside will only care about the outside, won't care about the inside, as far as the structure is concerned. You understand? Yeah. Okay. So back to settling. You know, this is some thermal imaging I took from my back wall this winter. We had settling on this. And that's the only building I had this issue. And it's the very first wall we've done. Is this not working as a system, or is this human error? All other walls on the building were just fine. It's certainly something to be very careful about. We, by now, blow these walls at a higher density than what we have done before. But that's something, you know, we will definitely need to monitor over the next few years. Is this good? No, this is a big problem. You know, there's a void basically which needs to be fixed. And this is, you know, my own building, my own crew did this.
Why not fiberglass going in?
I mean, cellulose is much better material, in my opinion, in a cold climate like this, for, you know, the qualities of the insulation material, for embodied energy, and for costs. And in a thick wall like this, even if you blow it with fiberglass, you can run into the same problems. It's, you know, we have to come up with a process on how to do this better, which I think where we are now. But the learning curve on the first building was certainly fairly high.
How are you checking your density in the wall? Just by feel and experience?
Yeah, there's feel and experience. I mean, there's a test you can do, but we're blowing it at 4 pounds per square. And again, you know, I have to really revise you on the report where we'll go into this in detail. I worked with 4 manufacturers by now and trying to come up with best practices for doing this. Something I'm working on. It's definitely a huge concern. But to me, you know, that's why I put it in here. Mistakes, we need to be careful, for sure. Application, something we do in-house now too in our buildings, just to control that better. But new building systems, new challenges. Yep.
In your, oh, sorry.
Can you pick apart what you've got there? Is that the red to the far bottom right?
Yeah, this is basically voids in the insulation. You see heat loss from the building because there's a void in the insulation. You know, the blue part that's how it should look. Very little heat loss.
Right, but then the bottom right, is that just, you think?
This is basically the same. We're looking at the same. It's just a blown up. Just to confuse you, I blew it up a little more. Yeah. Yeah.
What's the height that you stack that to?
Yeah, this is 2 stories tall.
Right, so do you have a baffle to?
No, there's no baffle in it. The whole principle of this wall is so they can settle in. It's overblown on the top. So something like this should not happen. However, it happened here. Why? I haven't figured it out yet. I'm gonna, you know, tear this apart in the summer and figure it out.
Municipal code here just now, they've torn up some old buildings that had cellulose put in 50 years ago. Found very little settling in most cases, but it was probably only an 8-foot high wall. And
yeah, I mean, there's
even here,
cellulose has been used for many, many years. It's not, there's nothing new about it. It's just, you know, in the wide cavity insulation like we're looking here.
The weight helps?
Yeah, I mean, the weight, you know, just think about the weight pushing down onto it. So, you know, by rights, the way it is designed, you know, it shouldn't do this. And this is, to me, human error. You know, it's the bus driver killing everybody driving off the cliff.
So do you have an open space at the top of it?
Yeah, it's completely open on the top, and we blow that extra height so that it can settle in. Yep.
That's great.
Yep. Yeah, that's the way it is designed. And you know, the cavity now is much wider than it used to be on the first building. On the first building, we insulated the inside. We went with 2x6. Now we make a wider cavity, which allows, you know, for better application. We actually can get a person in this wall to blow it. That's how we do it. Really, we get one with a hose, and for 2 days we blow this wall out.
You add more now?
Yeah, I mean, on this one, you know, I'm just going to have to take it off and blow it back in. I mean, it's not the end of the world. But it's something, you know, we definitely don't want to see on other buildings. You know, that's where experience comes in. So let's keep on. We're going to run out of time. Windows basically are really the key, in my opinion, for building these high-efficient buildings. Here again, our energy modeling software. Our goal needs to be that through windows, we're gaining more than we're losing. We can only do this in our climate with thermal shutters because we cannot build good enough windows. But this is the crux. We need to gain more energy from the sun than we're losing in windows. Again, we need to look at the sun paths. We need to place windows where they belong in the south. Hardly any windows in the north if we can avoid it. Completely eliminate them. We can do through lighting with transom windows for daylighting. I use big, clear glass panes on the south-facing side, basically like here as an example on our living room. This is a window 16 by 16, basically, 16 feet by 9 feet tall, with a little ventilation window on the bottom.
Does that mean no coatings? No e-coatings?
No, I mean this is this application here was a heat mirror. We've gone away from that. We're using cardinal glass now, but it basically means we're trying to focus on this, on the solar heat gain coefficient, the free energy we can get in. Ideally we would want to have 100%. If we only have a clear glass, basically 100%, no coatings in it, our U value, our R value of the window is very, very poorly. So we're trying to find balance. The best balance I found is to try to achieve anywhere between 55 and 60% on the solar heat gain coefficient on the south-facing side, with a U value, as good as it gets, and then put a thermal shutter in front of this window to overcome the problem of the heat loss when there is no sunshine. Unfortunately, technology is not there. We can have this. We can either do high solar heat gain coefficient, or we can do high U value, high R value. A lot of the windows, which are sold in the stores for our climate, they have a solar heat gain coefficient of 20. They're ideal for California. They're terrible for our climate. People only look at U values. They don't look at solar heat gain coefficient. Then placement of the window. Where are we placing the window in a thick wall? That is a huge ongoing discussion, which I'm very tired of. It's called the Innie versus the Audi saga. So, basically, are we placing the window on the outside, like we usually do on buildings? Boom. Well, now we have a 24-inch thick wall. Oops. Where are we putting these windows? Or are we placing them on the inside? Or what are we supposed to do with these windows? So. Again, I've learned this the very, very hard way. I built thicker walls, placed the windows on the outside because that's what you do, and then I ended up with a lot of icing and a lot of problems. And I'm still dealing that with buildings which I have out there. There's not enough warm washing from the building anymore. It can't reach that window. The window sits all the way in the cold side. It's stupid. Unfortunately, at the same time, when I realized this, Passive House released their 2-year-old study. That window placement is really crucial. Windows should be placed 40 to 60% within the wall cavity, and we also should over-insulate these window frames. So if we're looking at this window as an example, it looks like it's all the way on the inside. However, it's a 24-inch thick wall, so this is just halfway, 50%. Forget about all the formulas. This is what you want to remember. You increase the efficiency of this window by 20%. For free by placement of the window within 50% of the wall, and by using basically over insulation. I do it on both sides. The frame basically is what really our main heat loss is. The edge loss basically is always the greatest. We see it on a thermal image here later. And it's really nothing else other than putting a fir hood in front of a window. Fir hoods, again, indigenous wisdom. We figured that out 10,000 years ago. We create a pocket of warm air in front of where we look out. It's exactly the same thing. It's so simple and it works so well. And we can save 20% of the energy on the weakest link of our assembly. So, yep.
I was wondering what the difference between 40% and 60% is.
This is basically what I'm trying to explain here about balance.
I was just going to ask how much
it's
do you need on that?
It's balance. We need to find a balance between a few things. We have one core problem, daylighting. The further we place the window on the inside, where we thermally would be better, bigger fir hood. However, what happens is we are limiting basically how much solar radiation we allow into the building because of our shading from the wall. The thicker the wall, the more dominant that becomes. So really, that's why 40 to 60% is a balancing act. For what we've tried over the last few years and monitored, 50% works best, in my opinion. But this is really the thing to remember. This is, the shading we're getting, depending on also summer, winter, sun angles. We are fortunate enough when we need it the most, the sun is really very low and we get it right into our buildings. It makes a huge difference. And then we're creating this warm pocket of air, standing still air. It's huge. It's a huge difference. This cold air does not wash away this warm pocket. And it's really amazing to see how well that works. And then on top of that, a thermal shutter on the outside, and it works wonders.
Like how much dimension do you need to get that warm pocket?
Of depth. That's a good question. We're at 12 inches right now, and I see a huge increase. What's the minimum for that? I would say the minimum would probably be in about 6 to 8 inches. 8 inches probably, realistically, because of the wind washing into the pocket. This is the thing to remember. You have this wind washing on the outside of the building, and somehow you need that pocket here.
So if you had an 8-inch wall, would you still go 60-40?
Good question. You probably would want to go more to the inside on a wall like that. However, if you're only building an 8-inch wall, you are in a much milder climate, and it's not much, it's not as important.
Or windy climates or size of window.
Yep. The bottom sill, we slope at 15 to 20 degrees to allow water to shed out. And then, like I said, we place insulation over the frames on both sides to warm up, basically to eliminate heat loss on the edge of the window. And then we're still allowing for window sills on the inside. People always enjoy windows.
How far into the spacer do you do that? Do you find that insulation is?
Well, I use a tilt and turn window, which goes to the inside, which has the thicker frame on the outside for that reason, also for the air tightness.
Built into the frame.
Yep. So, but yeah, we over-insulate about an inch over the frame, basically. But that's really, the window frame is your defining factor for that, what window you're using. So, but I can't stress this enough. This is really huge. Even in a not quite as super insulated building, window placement can make such a difference. You had a question?
Yeah. Are your windows fiberglass?
Yeah, I only use fiberglass. I have not found any other material for our climate which is stable enough to eliminate the flexing in the frame for air tightness.
Replace when they're stuck in like that with vinyl.
Yeah, I've done vinyl before too. You can do it the same way, but for really cold climates, it's just too unstable. One winter at 40 below, that frame is flexing so much that all of your air sealing you have done very carefully is ruined, just because of the deflection. You get 40 below here and you get 70 degrees there. We have the Arctic and we have the tropics on a space of a window. It's extremely stressful on these frames. And then sometimes we have temperature swings from one day to the other, from 40 below to 20 above. Think about the forces on these windows. It's tremendous. So really, for our really cold climate, fiberglass is the only material I found which is stable enough for windows. A couple of shots here, you see the edge loss really dominant on this window on a thermal image. These are the plywood bucks basically we built where we place the windows. That's the 15-degree slope. So that's all built into the buck, and we keep it straight on this side so the window placement is easier. And then we built custom flashing for it on the outside.
3/4 plywood?
No, this is 3/4 inch plywood, yeah, this is metal. And then this is air sealing tape on both sides. We have a special air sealing tape we use, one on the inside, one on the outside, which is specifically made for this application, which comes from Switzerland, has the right permeabilities. We have a very impermeable tape on the inside with a 0.1 perm and a 1 perm on the outside to allow drying potential within the insulation to the outside.
Sticks okay to the plywood?
Oh, this stuff sticks to anything.
Do you have
It's
anything
incredible.
between the tapes?
Well, yeah, it's spray foam basically for insulation. Yeah.
Brand the window?
We use local windows, Greatland windows in Fairbanks. Yeah. Yeah, I'm very happy with them. They're
Is it
local.
what used to be Alaska Window?
No, it's a new company. It's a tilt and turn. It's German hardware. It's 7 lock points. And you know, I spec out the glazing to what I need. I mean, we glaze every window differently. In the south facing, west, east, all of the windows are glazed specifically for the orientation. So they're glazed differently. And that's important to have a window manufacturer who works with you on that for high performance buildings. So I can't stress it enough, really. Please, if you build buildings like that, place the windows where they belong. And then the big crux for our climate, the thermal shutters. This building could not reach passive house levels without thermal shutters. We cannot reach such an efficiency level without thermal shutters. That's really the weak link. And it shows it really well on this thermal image I took this winter. So this is this big window. These are upper windows. You can see the wall. It's very well insulated. You see a little bit on the collectors on loss, but overall very good. Again, the darker the color, the more the loss, and especially on the big window, you see the edge loss I was talking about. Much more drive. Now take a look at this, and then this is taken basically the next morning with the shutter closed. How much of a difference this really makes. And this big ugly thing here is a 1,200-pound shutter. It's extremely heavy, which closes right in front of this window.
Cellulose insulation again?
No, this is spray foam. You can't get, would be way too big.
Between the window and the shutter?
No, there's absolutely no problem, none whatsoever. I was very worried about how to air seal this. I put it up and it worked like a champ. I've never touched it again. So there's no air sealing done whatsoever between. It's tight, yes, but it's not air sealed. Like on old shutters where we've tried this before, where the windows were on the outside, where we had all of these problems. With the windows inset and this warm pocket of air created, this works really, really well. And I mean, it's a day and night difference. That was one of these big questions when we did this building. How much time are we going to use it? Is it going to be too awkward to use it? People behavior, what's the real value of placing a shutter on it? But if it's cold outside, this shutter is closed as soon as the sun goes down, because you're feeling on the inside how this heat sucks out of the window. The minute we close the shutter, especially in the evening when we fire up our masonry heater, it's a day and night difference. So it works extremely well.
So it just fits right up against the window trim?
Yep.
The wood?
Yep, it's really tight.
And
it's just on a track, basically.
You have to go outside to push it?
Right now, my wife kicks me out. I close it. Yep. Yeah, but it's going to be automated, so it's all wired for it. I just haven't gotten around to do it.
1,200 pounds?
Yeah, with a gate opener, it's really simple. I mean, we've done some other projects now. We just place a gate opener on the bottom and put it on a track. Works really well. It's not all that expensive either, really. It's fairly simple. It's just how to come about all of these ideas. That's the main problem I find. So if you're looking at this thermal image, the windows are really the missing link. That's our key problem we're having. So that's what we need to address. Unfortunately, there's nothing on the market right now. There's no commercial project. Yeah.
Is the big window the only one you use to shutter?
No. We're looking at this right now. You can see on this here is closed. It's an internal shutter. One of the things I've done on this building, basically, because of costs, I placed most window shutters on the inside. Because I figured, by the time we come up with some mechanics to operate them on the outside, it's going to be too expensive. Out of all of the mistakes I've done on this building, that was the biggest mistake. They should have not gone on the inside. I spent way too much money building them, and we are not able to control icing on these windows. We tried very hard to air seal as good as we can, but I mean, you can see on here, there's still loss. And if it gets 40 below, we get icing on the windows, which we have to chip away, basically. They still work as far as thermal performance goes. However, it's just icing problems we're seeing on the windows. Also, building them was a lot more complicated, a lot more expensive than I anticipated. It was a major pain. It took us about 3 weeks to figure out, how to actually build them, how to actually make it work. It was a huge pain, and then in the end, we have icing problems on the inside. So now we place everything on the outside, and I can't stress this enough. I mean, looking back was a big mistake, was an obvious mistake, but they need to be on the outside.
Are you using steel spacers on the glass?
On the glass?
Yeah, the steel spacers in the middle.
No, they're...
It looks like that one on the left looks like a steel spacer. Not a high efficiency.
On the window?
Yeah, on the glass itself.
Oh, that's the, there's basically 2 stainless steel spacers with cork in between because it's heat mirror. That usually...
heat mirror can't use the...
Yep, that's because that's heat mirror on this one.
Right.
Yep. Yes.
So no interior. What else?
Yeah, no interior shutters. I mean, on this building.
I mean, is it? Do they not work well?
No, they work. They work.
Because you tend towards more perfectionist sort of stuff.
No. I mean, they work. Thermally speaking, they work perfectly fine. However, you're icing your window when it gets really cold. So you're creating ice on the window. You are dealing with it every day. You have to get rid of it. It melts when you open the shutter. And then it creates a puddle of water on your windowsill, and over years, you create mold problems. It's just not a good situation.
It's like curtain closed.
You're trapping
I mean,
inside air when you close.
Exactly. There's just so much airspace in between, and then your relative humidity level drops to dew point, and the dew sets up on the window. The window is cold. I mean, you open the shutter, it's like you open a freezer. You close them for an hour and you open them again. They work really well, but you have an icing issue. If on the outside, none of these issues appear. So it's just how do we make it work? So I have several prototypes we built now with micromotors, basically, which just a push button, which close basically in front of the windows.
And the air tightness is not so key on the outside.
Right. It's much better performance from what I've seen on other prototypes. So, like this building here, we're placing everything on the outside. Everything is controlled by a building system, by daylighting, so it can be automated. And that's really where they need to be, just on tracks. It's just a matter of designing the building so that all of this fits, which is sometimes very difficult, to make space for that shutter. But I really believe for high-performance buildings, at least for Fairbanks, we really need to place R20 shutters on the building. Otherwise, we're really shooting ourselves in the foot as far as performance goes. I mean, without thermal shutters, if we're looking at this building, I did this exercise for this prior building here. We're looking at basically 13 kilowatts per hour per square meter. So we're reaching passive house level, which would be 15, no problem. If we're looking at our lines again, this is our dominant line. And then here the bar chart. This is our gain from the windows. This is the loss from the windows. Now we're removing the shutters. This is what happens. Exactly the same model, exactly the same building, exactly the same window. The only thing we're doing, we're removing the thermal shutter. So we're dropping from 13 to 20 kilowatts per square meter. And this is our loss, much bigger than our gain. And that's basically reality. Without thermal shutters, we cannot get to passive house level in our climate.
Just wondering about, if it's a cloudy day and you don't have direct sun, is it worth having the shutter open?
Daylight, yeah. I mean, you still get, like with regular daylighting, you get quite a bit of irradiation out of it. We don't quite think so, but it is really. The minute you have good daylight, you're much better leaving it open. Of course, also for human health. We need light in buildings. Big windows, especially in the wintertime when it's not very light out. The minute daylight is up, we open all the shutters and let daylight into the building. But the minute it gets dark and the sun is completely gone, we close them, basically. So.
Do you recall the square footage of windows on there?
Oh boy, what was, top of my head, I don't remember. But it's basically, this south-facing front here. This is what you're looking at. So it's huge. If you're looking at the efficiency level, unfortunately, that's the truth of it. We're really stuck with thermal shutters until window technology gets better. And I spent a lot of time, I traveled to Europe quite a bit, and I talked to many of the high-performance window manufacturers in Germany, you know, to look at options. What can we do? We experimented with 5-pane windows and trying to come up with solutions, but we're losing the solar heat gain coefficient, and you know, we are basically giving away our free energy as it stands right now. You know, in maybe 5 years that might be different, but for now, the low-hanging fruit really in the buildings is on thermal shutters. Also for retrofits, think about a lot of these buildings, you know, we're trying to bring up the buildings up to snuff, and placing a shutter might be a very good solution for a lot of these. And that's nothing we really look at too closely yet. So, this is a super insulated door I've built and developed. It's an R60 door, has 9 lock points. It's super efficient, you know, but this is what happens at 50 below. I can't get in. It freezes shut. So one of these things, you know, you think you have it all figured out, but then one little piece of steel ruins the whole day. And I still haven't found a manufacturer to make me a graphite piece for this. I know it's a very efficient hardware, a lot of locking points, but it's one piece of steel which just kills it when it's getting really cold. So that's challenges of our climate.
What if it just didn't latch?
Yeah, right.
You can get a positive fit.
Yeah. So it's very unfortunate. And you go through Germany and talk to these manufacturers of this hardware, and you explain this to them, you show them a picture, they look at you like you're totally crazy and you're from Mars. You know, you're like, you're serious? Like, yes, I'm serious. You know, so they don't understand. Thermal mass, I'm a big believer by now in including a lot of thermal mass in my buildings to even out temperature swings. Overheating in the summer. Again, our bar chart here, we don't see much on this. It's very difficult to model thermal mass in buildings. On this building here, we've placed 180 tons of sand under the standard slab. This is basically what you're looking at here. We're using that for additional thermal storage, basically, for temporarily being able to store more passive solar gain. Sun beams through the window, and we try to catch it.
In a slab?
In the slab, yep. So
that was
here's,
not your house, though?
Yep, this is my house. Yep.
Oh, but on your earlier slides, you showed foam?
Yeah, that was a newer, the wall picture I showed earlier is from our new design. This is the old design.
You did pour concrete floor?
Yep, on this one here, this is how we went about it, on my building. Yep. So here's our big window. We can see the daylighting, you know, the sun beaming into it. And this is really what heats my building since mid-February. You know, this window, this big slab, keeps basically this thermal flywheel going to maintain a 68 to 70 degree temperature even at these cold outside temperatures. You know, we have enough storage capacity to bridge time, few days, to allow when we have no sun for the building not to cool down to a level where we have to heat. This is about a 1-week thermal flywheel which we create. And it's, you know, a fine line of calculating out your mass over whatever else. So very simple, no maintenance ever, very, very basic, and it works really, really well.
Are you also heating that with hot water thermally?
I can thermally load this, correct. In the fall, we thermally load it with the collectors to store additional about 2 million BTUs in the building. You wouldn't want to do this any other time other than in the fall because you overheat your building otherwise. You know, it's heat in, heat out. There's no control, no thermostat. This is just quickly here. From the sensors, we can clearly see also the passive solar gain on how we store energy on the sensors. And then annual heat storage. Last but not least, you know, the big question, how do we bridge this 3 months of nothing? This is unfortunately reality for us in the dead of winter. When we need the heat the most, we have none available. What a bummer. So heating is our problem in our climate. There's just no way around it. This is very specific to the really hot northern regions. You know, in other climates, this is a little bit different, but for us, this is really the thing to remember. It's all about heating. And On this building, I used 480 square feet of thermal collectors. That's basically 12 collectors, 4 by 10, and they're flat plate solar collectors. What I found in Fairbanks is that flat plates work better than evacuating tubes because of the icing. We don't have enough off heat on evacuated tubes, and they ice up too much. When we need them the most, they don't work anymore. Versus flat plate, they are very inefficient as far as energy loss goes. So they're producing enough off heat to melt that ice off, and then they function. So I'm a big believer in flat plates for my climate, also for the simplicity of it. We're actually building a lot of these now in-house big systems ourselves because there's nothing to it. It's just copper pipe and some fin tubes and some glazing. So we're reducing costs quite a bit. For bigger systems, they're 32-foot by 10-foot collectors, one unit. So we don't have all of these heat losses on all of the individual collectors. The biggest cost for most of this is transportation getting this here. So building them locally will be a big saving, at least 40% saving in my opinion. And it's very basic technology. There's nothing which can go wrong. We have collectors like this on roofs for 60 years, which still work. We're just circulating fluid. One of the biggest lessons learned on this building was it was a pressurized system when I built it. So it was always under pressure, and I had way too much heat. I never knew what to do with my heat anymore. My heat storage capacity was underestimated, so I had way much more heat produced quickly than I thought I would. And I didn't know what to do with it. So I always fought it, what to do with my heat. What a problem to have. You're creating too much energy. And I converted it last spring to a drainback system. So the system only comes on when there is demand. Otherwise, there is no fluid in the collectors. And that solved all of my problems. It's definitely all of the new systems we design are only drainback. It's simplicity, and no idea why I didn't do this to start off with. I have absolutely no issues on the drainback side. And as far as collection, we need more collection if we want to heat buildings with this in the shoulder seasons. In the summers, it's definitely, we don't need that much just for producing the domestic hot water. But right now, for heating or for late fall, when we try to heat a building, we need that additional storage capacity, that additional heat.
Would that overheating just happen in the summer, or?
No, actually it happened right in March.
Really?
Yeah. Oh yeah, I was melting out my yard in March. I used my heat dump for the system was my loop from the ventilation system. That's what I used for a heat dump. And I ran it every day. I melted out my yard. I mean, I could have supplied heat to 3 other buildings in the neighborhood. I mean, it's phenomenal how much heat it produces.
So how do you increase your storage in March?
Of course, we could increase storage, no question. If we had more storage, it's the feasibility of it. I talk about this here in a minute. But as far as do I have too much collection for my storage? Not really, because when I really need it, the spring is not when we need it, it's in the fall. And our highest solar irradiation is in April. April, when we don't need it really, we get the most energy. In the fall, we have much less solar irradiation. And that's where we need it, because we're going into winter, we're going into the heating season. That's where we really need to plan for. So it's kind of an oxymoron, unfortunately.
We're twice as much sand.
Yeah, but as far as sand goes, it's very hard to control. Water is much easier to control and do things with. Yep.
Are you going to put in a pool in next time?
Yeah, I mean, that's one of the things, there's several other things I want to experiment with, and I have plenty of extra heat to be able to do this. Unfortunately, I ran out of money to be able to do this. Building an external garage is on my agenda, which will integrate, a ground-based storage system. How can we, create much bigger storage available on a low-cost means?
Solve your block to your problem.
Right, exactly, absolutely. But unfortunately, I ran out of money, so I'm sure everybody can relate to that. So seasonal storage, we have an upright container. That was one of the big lessons learned. The first buildings I've done, we placed tanks basically besides or under the building. The problem with that is on our residence, we have so much hot water needs during the summer, and the amount of hot water we need to keep in a container like this is much higher than when we place it upright. So on an upright container in the middle of the building, we're only keeping the top in the summer at 120 or 140 degrees to make domestic hot water, basically. So much less energy requirement. And then think about it, this is a tank living inside. It's super insulated, so we see the framing around it. It's dense packed cellulose at R70, basically. We're placing the heat on in the inside of the tank. The heat loss from the tank is first in the building as a BTU available for heating. So for energy balance, it works really well for our climate. So an upright container centralized in the building, that's basically the way I design these buildings by now. I place it somewhere in the center. I place my masonry heater in front of it, and then the big window basically is utilized in the front. And then collectors are very close. We can get the heat into this container very simple and easy, very quick. And it functions extremely well. It's, to me, pretty mind-boggling how well this system really works. If you think about that, you can make all of your hot water and your heating for 9 months out of the year with, half the energy of a light bulb. How cool is that? Yeah.
How big is the tank?
5,000 gallons. Yeah. The size of the tank really is a mathematical equation of time. How much time do we want to bridge? For our climate, if we want to bridge 3 months, we need about 1 million BTUs per 1,000 gallons of water if we are loading at 160 degrees. So we need massive amounts to bridge completely. And it's not really feasible to place it in a building. I haven't found at least a solution for it. Here I went with a compromise of 5,000 gallons. For several reasons. Space, as far as, we're giving away space in a building. We're giving away the purchase of the system itself. Here, it's a readily available tank size, 5,000 gallon used tanks, or you can buy a lot of them for very inexpensive. I paid $1,000 for this tank. So there's no money really into it. And by now we're building most of them with ICFs. And I have a manufacturer who builds these heat liners, which I place on the inside. It's basically a 60 mil plastic bag, which is specifically made for heat application, which has a continuous rating of 200 degrees, a lifespan of about 15 years. So we place a manhole on the top, and we bolt these bags more or less on the inside. So they can be unbolted in 15 years, and we can replace it. We can put a new liner into it. A leaking 5,000 gallon tank in the center of the building is not a good idea. So it needs to be maintainable. But out of the whole system, there's 2 pumps at $248 a piece. And there's this liner, which was for 5,000 gallon. It's about $900. That's your replaceable items in 15 years. So the maintenance costs on the system, really, you have glycol, of course, which you need to replace every once in a while. But other than that, there's nothing else there. It's so simple. When you first start out, it seems mind-boggling how to design and build these. But now where we are, it's half the plumbing of a boiler, and there's no maintenance. There's nothing to it. And it runs on 48 watts. So, it's really, really interesting.
2 pumps?
2 pumps, yeah. It's water and glycol, so we have a plate exchanger, unfortunately, which we need to use. Ideally, we would want to run water, but at 50 below, that's a little scary. So, and the top of this is basically a picture taken from the bottom of the tank up. This is a stainless steel tank, which we custom built. It's a tank in a tank design. So we're making our domestic hot water basically in here. The line which you see here is basically coming in on the top, dropping to the bottom, and coiling into the domestic hot water tank. It's under house pressure, basically. It's the cold water coming into it. And then it's preheated from the mass of the big tank. And then the hot water is just simply made by convection. We have a large amount of hot water. As far as this tank is concerned, there's 800 gallons of hot water surrounding this little 40-gallon tank. And through convection, basically, it heats up that water. So it's very basic, so there's nothing really involved. It's just physics. And like I said before, I mean, we can shower, we can run 2 faucets on bathtubs wide open for over an hour before we lose 120 degrees, so it's working extremely well. And then it recovers, of course, within 15-20 minutes. It's not like this cools down. 5,000 gallons of hot water is like driving a freight train at full speed. That's the thing to remember. And it's just an awful lot of energy which we can use to bridge time. And to me, that's really for solar hot water systems, if you're looking at efficiency and paybacks, it's really the only problem we're having is the storage. The storage we designed for these things is too small. 100-gallon tanks, it's just not cutting it. We have days when we have no sun. 3-4 days, no sun. Well, we used up the 100 gallons the first day, and then we have nothing, and we fire a boiler again to do that. Here, we can go 6 weeks. I can go 6 weeks if I'm charged up without doing anything. I can turn it off for 6 weeks, and I have hot water for a family of 4. And so we can bridge these times when we don't have sun. The design in the middle here I call a solar stratifier. That was the big missing link for me to make this thing affordable. What is commonly used in Europe is basically 3 sets of coils. There's a set of coils in the bottom, in the center, and in the top. And then the solar controller basically loads the heat depending on the temperature it gets on the roof. In the morning, let's say we're getting 90 degrees. The bottom of the tank might be 40 degrees, so it's very worthwhile storing 90 degrees. Can we do anything with 90 degrees? For hot water? No. We need minimum of 120. However, in a building which only needs to be 70 degrees, 90 degrees hot water is pretty valuable. So we can collect much more temperature ranges, and during the day temperature climbs up maybe 120 and 160 in the evening, past high noon, and then they're loading these big tanks basically through these coils. The trouble with that is they're very expensive. I priced out stainless steel coils for a big tank like that. It was $24,000. So that puts a big dent into your wallet. This thing here is basically doing exactly the same thing. It's a standpipe of 8-inch CPVC, which goes all the way to the center of this tank. Everything is loaded from the top because I'm worried about leaks on the bottom of the tank. I only have holes in the top. And then I used 1-inch CPVC with a lot of elbows, 8-inch spacing basically, what you can kind of see here. And it's just basically using the physics and quality of water. Water changes its density and its qualities by different temperature ranges. So the water, when it's pumped in at very low speeds, finds its own weight and density within this tank through this solar stratifier. So when we're going back to the morning heat, 80 degrees is found down here, so this will drop into the stratifier and try to find its own weight and density just by physics, and works, luckily, really well. The big standpipe around it basically just eliminates the pumping speed. When it comes out of these tees, what we're trying to avoid is stratification of the tank. We want to keep different temperature ranges. So before it goes out and creates little swirls in the tank, it hits this big standpipe with a lot of holes drilled into it. It hits that and settles in again, and then drops out basically where it finds its own weight and density and temperature. So again, we're just looking at basic physics and basic laws of nature to make this all work. This thing, I can give you a parts list right now. You can go down to Ferguson for $860. You can build it. So $24,000 versus $860. This is a big winner for me. And I'm very happy with the performance of it. So the biggies so far, I used PEX for this pre-warming. It works. However, you get taste of plastic on hot water. So it's a bummer. It's 160 degrees in this tank for quite often, and that's too hot. So I'm going to get rid of this and replace it with copper, basically just for that reason. It works, but I would not recommend it. I would use copper. Another experiment I'm going to run here soon is replace this tank, basically. the cost of the tank and also the complexity of it is a little bit too much for me. And also the fact that we have mechanical connections within the tank scares me. You know, one of them goes out, you have a problem. I mean, we have an overflow protection and an alarm basically with a float in this tank, but nevertheless, simplicity, you know, I'm trying to make it simpler. So we're going to place just basically a copper coil to replace this little tank and run experiments on how performance compares. That will allow us to keep all of the connections out of this tank, basically. Everything else worked really well. If we are having a non-heating demand, only a heating demand, like on this building here, we have hardly any hot water we're making. This is a small public library building. The only thing we're really worried about is heat. So I place it under the building. Again, we don't need the stratification in this case because we're only concerned about water, and we can save valuable space within the building. So I'm not saying this is the only solution. For residents, I would always use an upright container, 2 stories, 3 stories tall. I mean, I just finished the design on 3-story tall tank, basically, for residents. But on a commercial building like this here, where we only place our concern on heating, it's very feasible to put it under the building. And you know, this is just an ICF. It's very simple to build. The same principle, we're using a liner in this. This is 14,000 gallons in this case. And you know, we could make this bigger too if we would have enough collection available. We need to keep a balance between collection and storage, of course. If we don't have enough collection and we have too much storage, then we're having an unbalanced system. And then again here, you know, this is a masonry heater which ties also into the same system. And then there's a little access hatch to be able to maintain it. And I guess I forgot to mention this. Of course, the domestic hot water circulates through 2 coils in the masonry heater. So every time in the winter we fire our masonry heater, this is where we heat up our domestic hot water. And then we're going the other way around. If the surrounding temperature of the big tank is maybe at 120 degrees, and we're heating this little tank up, you know, within an hour, we have 160 degrees in here, then we're heating up the big mass, basically, and we're keeping the storage so that we have hot water during the whole day, and we don't rely on a fire, basically.
Before, when you came last year, you talked about having an auxiliary heat pump, or?
Yeah, I removed that completely.
Okay, yeah.
Yeah, I got rid of it. Yeah, there was a backup we had originally, which I removed because I never used it. It's not needed. Yep.
On your new drain bag systems, are you still using glycol in the flat plate?
Yeah, certainly. For our climate, I'm too chicken to use just water. Ideally, we would only want to use water, but it's pretty scary to do in our climate.
A tank you want to drain into?
Yeah. I mean, in a milder climate, I would definitely recommend just using water. I mean, every time we use glycol, we lose efficiency. If we're using a plate exchanger between water storage and collector, we're losing 8% just in the transfer between the plate exchanger.
Do you know what the efficiency loss is to glycol?
To glycol depends on the ratio of the glycol, but you know, it's definitely in up to 20% easy. Yeah, no question. Yep.
What size plate exchanger? Is it just a regular?
Well, that's something you need to calculate. I mean, the plate exchanger I have is about that size. So yeah. But it's, again, you know, it's a calculation. It's fairly simple.
For average domestic.
Yeah, no, it's about that size. Yeah. And then again, you know, the house has. I mean, this is 1 tank. The controller looks at this tank as 4 tanks. So, you know, we're looking at the different temperature settings so we can store all of this energy. The key to remember is, you know, you're better off with a bathtub full of warm water versus a cup of hot water. Solar thermal systems usually only come on if they're reaching 140 degrees almost outside. We need a minimum of 120 for hot water. We need about a differential of 12 degrees before the collectors come on. So, you know, we need 140 degrees to be able to do hot water. And with the system I have, beginning of February at 39 below outside temperature, I already collect 140, 160 degrees of hot water off my roof. So like this morning when I checked my collectors, I was running steady at 168 degrees. So my big tank is going to be fully charged here probably by the end of March, which is pretty amazing. Water, I use water as my medium to store this energy. Think about it as a battery. It's nothing else. It's a huge battery, basically, where we're trying to store thermal energy. It's very easy. It's very simple. It's available to everybody. It's non-toxic. There's nothing to it. For our 3 months, however, it just doesn't have the energy density we really would need to be able to do annual storage. So, we're doing seasonal storage right now. We can bridge about 6 weeks in my house with the 5,000 gallons. If I would want to bridge 3 months, the tank would be too big. If we use different means, phase change, they built tanks like this in Europe already. And I'm really surprised that there is not more development in that direction. If we use phase change materials, we can easily reach a factor 4. Or, one German company, they're using a factor 8 now. They're taking these to freezing temperatures, basically, and extract it with a heat pump. So basically, this means, in a 5,000-gallon tank, instead of being able to store 5 million BTUs, we can store 20 million BTUs. Or, we can store 40 million BTUs. That's really when things start to make sense. This is, I think, right now the big missing link as far as being able to bridge this time long enough for our climate. And for the life of me, I don't understand why we haven't figured this out. If you look at the engineering required to extract oil from the northern slopes, mind-boggling. We're not able to store simple energy in a tank. So this is one of my core research projects right now. How do we feasibly store more energy in these tanks with different type of medium than water on a budget? It's all available technology is there, but it's too expensive the way it is right now. So
simply increasing the volume of water.
Yeah, that would certainly be feasible, but the costs are just storing like heat under a building, where we could use the unlimited amount of storage of the ground, if we could make that work. But latest studies I've seen from Europe about this is very discouraging. That's another project we're working on the research project, trying to model this on a bigger scale. How can we store all of this summer heat under a building so we can store, in the 40 million BTU range. I have a big commercial building I designed where I have a huge amount of thermal storage I'm placing under the building, but it's all insulated. And it's a big building. It's 25,000 square feet, so it's that's gives you a lot of footprint. So that gives you a lot of storage capacity right there, especially since we have to bring all of that in to bring the building up. So there's a lot of different opportunities, but in the end, this is, I think, where we really need to focus on for future research. And I think this is the key to remember. Whatever we build today can be an opportunity, can be something which will function in 5 years, and 10 years, and 20 years, no matter what costs are of utilities. Or it can be this, and this is basically 99% of all the new buildings we built today, not just necessarily here, but in many parts of the world. It's really this. It's a big liability. Any new building we built today in our climate, in Fairbanks specifically, people will not be able to afford to heat them in 5 years. They simply will drop their keys and leave. There's no way they're going to be able to afford it. And then what are we going to do? In a brand new building, we're going to retrofit. So let's create opportunities. There's extremely much we can still do. This is just stuff I do. There's so many more people, so much more smarter people than me out. If we all come together and figure out options, we can create real opportunities. And if there's one message I want you to take home, is this: we have no excuse not to do this anymore in our day and age. We're out of time, and what is our next generation going to do? We need to stop doing what we're doing now. The payback on a building like this right now, just the insulation, just making it super efficient, is 4.8 years in Fairbanks. That's nothing. Why are we not doing this? If we are going to almost zero energy, we can still be under 10 years right now. Why are we not doing this? There's no excuse. Costs, I always hear costs and costs and costs. If you're looking at true cost of ownership, there is no excuse, not in our day and age. And if we are really thinking that fuel prices will go back down to where we used to be, I think that's foolish. So we all can do our part. If I look at the few projects I've done over the years and the feedback I get from all over the world, it's mind-boggling to see how much we can really try to do as individuals. So let's be all pebbles in the pond. Each and every one of us can do something. And if we all do that, then a lot can happen. And we really, really need to understand that for us in the North, that will be our survivability. Power of community, us living in the North, will all depend on how we create sustainable life in the North. If we hit really high energy costs, people will move away. We will die out. I mean, all of our remote villages already have this kind of an experience. This is a picture of Savunga. If you're looking at this, this is very unsustainable, but Anchorage or Fairbanks isn't any different. Right now we're producing 1% of our own goods in Alaska. Everything is flown in. Everything is brought in. We're not going to be able to sustain that for much longer. So this is my journey so far, and I still see a lot of potential. This is a long ways up, but it's a long ways to go still. And I think we can really come up with a lot more good systems if we all put our minds to it. Yep.
How did you solve your thermal bridging over your insulation on the outer wall, right where the door is?
There's details. I didn't have a picture in here, but it's a fairly simple detail. I think on my webpage there's a couple of pictures.
Okay.
Yep.
Thank you.
Yep. But yeah, the thermal bridging basically is something we cannot afford. And like on door openings and whatever, it's crucial that we address them. But it's really simple. There's nothing complicated to that, really. Yep.
Do you have an approximate cost of the building?
It's like my building was $234 per square foot, which was more than I wanted. I could build it 30% cheaper right now with the lessons learned and the 5-6 other buildings we've built meanwhile. On average, our buildings are running anywhere between $184 and $300 per square foot. The $300 is, the $60,000 countertops we're installing for clients. As far as the energy package concerns, in the 200 to 240 range with all renewables, with everything. Any more questions?
Are you tracking anything like Carl Castle's place where he has both wind, solar, and solar hot water?
As far as percentage?
Yeah.
We still don't have a monitoring system on Carl's place, unfortunately. Something we're working on. But for an off-grid place, his house or his project is an off-grid, which is, the true zero energy. If we get this building to zero energy, then we really are there. Everything else is kind of cheating. And for a building like that, we need to have wind power for sure, to be able to do this. And there's quite a bit of wind which he really utilizes. But then again, we're really limited on sites with good wind. Most sites you have good solar, but you don't have any wind. So, yep.
In your wall system, if your outer fabric layer is properly sealed, do you have to have the plywood layer, or could it be replaced with a different?
No, there's no plywood on the outside. It's just a membrane.
Inside you've got the plywood barrier.
Well, that's your pressure boundary. Yeah, you can't replace. That's your structural sheeting too for the building to be structural sound.
You didn't need it for the shear strength. Could you use a different material?
Yeah, but to me, the plywood, the CDX, is ideal because it has the qualities of wood. It has the qualities of what I want it to be able to do, that diffusion layer, basically, that membrane layer. So I don't want to replace that. That's definitely a core product.
Is that diffusion, the perm rating, is that pretty, I mean, standard? Is it consistent through time?
It's a dry cup, basically. We differentiate dry cup and wet cup. That means basically how much relative humidity is within the plywood itself, the wood. The higher that is, the higher the permeability. If it's soaking wet, you know, you have a perm of 50.
Manufacturers, can you trust that it's...
Yeah. Yeah. On a dry cup, on a CDX plywood, you're looking at about 0.6. And then, you know, once the wall reaches a certain relative humidity, you're looking at about a perm 1. And then it fluctuates depending on how the state is on the inside versus the outside. So.
Do you think the diffusion concept would work on a 12-inch wall as opposed to 18 or 24?
Yeah, I mean, it's all climate. The diffusion, you know, that has nothing to do with the thickness of the wall. It's only about air tightness. It's only about air tightness. You know, we're not allowing air exfiltration. 99% of all of the structural building problems we have is air exfiltration. Air tightness is really the key. But the insulation level really doesn't affect that. That's the air tightness. We got to make sure we're airtight. And that's a process. You know, we have to fluor or test during construction. We have to make sure we're staying, you know, on an airtight level. Yeah.
What other people around the world have done this diffusion open wall?
Well, it's very common in Europe. It's very common in Europe. In Germany, in about 5 years ago in Germany, it was mandated by building code that any new building system which is put up needs to be diffusion open, which was a $24 million study from the Fraunhofer Institute. Basically, for many years they studied this, and they concluded we cannot build anything perfect. So it's mandated by building code in Germany as an example. So it's very common in some of the European states with modern building science.
So I think a lot of people, when they first hear this, they think that you invented it.
Oh no, I have no invention. I take no claim in any of this.
Yeah,
for sure not.
That would be a good point to bring up.
Oh no, for sure. No. I mean, I'm just putting pieces and parts together what other people have figured out.
And they also use structural sheathing as the perm layer.
Yeah.
Not a membrane of some sort.
Yeah, I mean, some use a membrane, but it's very common to use plywood. Yep.
What would be the possibility of, I don't know, has it been done for retrofitting existing structures with an open wall?
You know, for open wall, retrofits are difficult. Yeah, that's where the biggest challenge is ahead of us, you know, how to retrofit buildings. If you go on Cold Climate's webpage, you find a study which was concluded just a few months back on retrofits on wall application, which was pretty interesting with some of the results. For diffusion open wall, you know, we're really looking at a system redesigning from the beginning. So you might create a lot of problems if you're trying to go there with something which is halfway there but not. You know, we can't go halfway. We need to have a system which really works. So you might be better off just to stick to you know, one direction. But it's a case by case for retrofits for sure.
Interior paints with this system? Interior paints on the...
Yeah, I mean, if you use a very, I mean, that's, you know, an ADA, like an air sealing through the paint and sheetrock, that's certainly an option too. You know, we use something which allows diffusion. You could use a primer, which is a class 1 vapor barrier, basically, to seal off on the sheetrock side. However, it takes away that buffer capability, which I'm after, for being able to create healthy human environments.
So what do you use on your buildings?
We use VOC-free paint, basically.
And standard drywall,
yeah,
and all that.
Yeah. I mean,
there's enough permeability.
Yep, there's enough permeability. Yep.
This question about the cellulose and what they actually, I mean, it's a recycled product, so there's whatever inks, dyes, naturally in the product, but also they add fire retardants.
Yep.
Having a breathing wall that has these chemicals and what, are there any concerns about that?
Yeah, I mean, there's chemicals. You can eat cellulose. You couldn't do that with any other material. Is it 100% natural? No, for sure not. Are there better products? Yes. Do we have them available here? No. Right now, at this point in time, to me, that's the most sane material to use. But I mean, it's certainly valid. I mean, there's in Germany a huge movement is biology. Basically, you know, we're looking at what's really healthy in buildings, and I mean, it's amazing to see what they're going through to get to building materials which they can sign off. You know, they're using a lot of very innovative means of getting there, and we're certainly not there with what we have available. Would I prefer cellulose over spray foam on the outside of my wall? Yes, I would. Indoor air quality, what we monitor, is very good. We don't see any, you know, bad outgassing out of the cellulose.
And on the outside of...
Yeah. And, you know, again, we always saying breathable wall, but it's really wrong to say breathable wall. It's diffusion versus, you know, on a diffusion level, you're looking at a very different molecule level. The air tightness level is between your insulation and your interior structure. So you, by rights, you should not be able to get anything in there because it's on a molecule base, on a diffusion level. Yep.
Did you ever hybrid your system, throw a couple of photovoltaics in to turn a meter backwards?
Well, you know, absolutely. I mean, my goal was from the day one, I wanted to have a 5 kW photovoltaic system online. I ran out of money. That's the only reason it's not there yet.
You're off grid then?
No. I'm on grid. Yeah, so I just sell back to the grid. It's fairly simple. But yeah, no, the only reason I have not done that yet is money, unfortunately. I'm very upset about it, but can't do anything about it. Got to go to work, make more money. Yeah. I spent a lot more on this building than I first thought I would. A lot of experimenting. So, yeah.
Well, thank you. We got to go to Wasilla to do another presentation, so thanks.
Okay, thanks.